Hello, my name is Matthew Rex. I was supposed to teach a class Monday and I apologize. I forgot. There's no excuses. So I'm sorry to those of you that went to class and waited for 10 or 15 or 20 minutes. I apologize for wasting your time. I apologize to Dr. Kubler, who expected me to be there, and sadly I wasn't. To try to help at least a little bit, I'm going to make this short video here covering what I would have gone over in class. So hopefully you won't be behind. Hopefully Wednesday, you'll still be able to start lecture where you were going to originally. And hopefully this video will be helpful. You can pause it, stop it, play it faster, slower, whatever, rewatch it if you want to. So you're starting on electrochemistry. And if this will, there we go. So you're going to go over revisiting those redox reactions that you've looked at in previous chapters, at least a little bit in 2045. And you're going to look more specifically at them, focusing on the flow of electrons and how can we use that flow of electrons to do work? How do batteries work? How can we store that energy? How can we use that flow of electrons to move a car, spin a motor, things like that? And electroplating, things like this up here, you can see in the top right. So the study of chemical and electrical energy. So if we have that redox reaction, we have a chemical reaction occurring, and we have a flow of electrons, then within that, it's going to give us that electrical energy. So yeah, we're looking again at redox reactions, and we're going to look a lot more specifically into them now. And then how can we use spontaneous redox reactions to generate electricity, or non-spontaneous reactions to make use of certain specific chemical reactions? How can we put energy in that to drive that and get some benefit from that? So again, oxidation is the loss of electrons. Reduction is the gain of electrons. You have all kinds of different little mnemonic devices you can use. You can use Leo, the lion goes grr. So Leo, loss of electrons, oxidation. Grr, gain of electrons, reduction. You can do oil rig, whatever you want to do to help you remember that. And these do not occur separate from each other. If something is losing electrons, there has to also be something there to gain them. So we're going to see within a reaction, identifying different oxidation states, seeing that those oxidation states are going to change. One of the oxidation states is going to become more positive, and the other is going to become more negative, and that's going to show us what's gaining and losing electrons within that reaction. So in this case, we'll go over in a little bit, again, how do we assign oxidation states to these, every individual element within a reaction, and the reactant side and the product side. And then, of course, how can we determine from that what's being oxidized, what's being reduced? In this case, we'll see the manganese has an oxidation state of +7 on the reactant side and a +2 on the product side. So to go from a +7 to a +2, it became less positive or more negative. It had to have gained electrons. And in this case, to go from a 7 to a 2, it gained specifically 5 electrons. Lost. No. Yeah, gained 5 electrons. Sorry. So it was reduced. Therefore, this is the oxidizing agent. We'll get into that, maybe oxidizing, reducing agent more too in a second. And then within the iron here, we have iron 2+ going to 3+. So it became more positive. It lost electrons. So the manganese was reduced. The iron was oxidized. To identify the oxidizing agent and the reducing agent, those are always on the reactant side. The oxidizing agent is the thing that facilitates oxidation. Since oxidation is a loss of electrons, the way it's going to facilitate that is it's going to be the thing that's gaining electrons. So it's this manganese 7+ that is the oxidizing agent, because it's going to be reduced to manganese 2+. It's going to help facilitate oxidation. So this technically, maybe the whole thing, the manganate is the oxidizing agent. And here, the reducing agent is the reactant that facilitates reduction. So therefore, it's the thing, since reduction is the gain of electrons, something has to provide those electrons so something can gain them. So the reducing agent is the thing that's being oxidized, because it's providing those electrons for the reduction. So this Fe2 plus is our reducing agent. All right, so again, I talked about how we have to balance this. We have to have naturally balanced reactions anyway. We have to balance all the elements that are present. We have to stick to conservation of mass. We can't create matter or destroy matter or anything like that. So we need to make sure those are balanced, that if we have one manganese on the left, we have one on the right, the number of irons match, etc. But once we have that, we have to account for where are these electrons going, what is being reduced, what's being oxidized, and how can we account for all that. So here, we're going to take a couple example reactions. Actually, let me go back to that, write it down. Sorry. So we're going to look at this one for starters. Okay. So there's a few different things within this. We need to assign oxidation states to everything. We need to figure out what's being oxidized, what's being reduced, and we need to balance these eventually within either an acidic solution or a basic solution. And the problems are going to tell you that. They're going to let you know which of those two it needs to be. So we're going to look at this first maybe in its most basic form. So we're going to have MnO4 minus plus Fe2 plus going to Mn2 plus Fe3 plus. So you'll notice, of course, there's some things here that still don't balance. We're going to say that this is balanced in acidic solution. The first thing I want to do again is figure out what's being oxidized, what's being reduced, what are my oxidation states. And these go back to your earlier chapter in the book, I think it was 5 or 6, that covers how do you assign oxidation states or oxidation numbers, and what is chapter 5, I believe. There we go. Let's see, guess. Yep. Perfect. So, few rules that go with that. So this is on page 195 of the 5th edition of the General Chemistry textbook by Tro. You have rules for assigning oxidation states. You have 5 rules. So the first one is any atom in its naturally occurring state or as a free element would be 0. So for iron, that's a metal. That would be iron and solid, not ionic, but just solid metal iron. And we don't see anything like that in this problem. So we don't have anything that's going to start out as a 0. Next, a monoatomic ion is equal to its charge. So what's mono? Single. So single ion, Fe2 plus, Fe3 plus, Cl minus, something like that is a monoatomic ion. And whatever its charge is, that's its oxidation state. So I have this Fe2 plus that has an oxidation state of +2. Manganese is also a monoatomic ion. It's got a 2 plus charge, so its oxidation state is +2, and the iron is +3. So regardless of how many of these there are, if there were 2 irons for some reason here, I like to write just the oxidation state of an individual atom. That's going to make it easier at the end, I think, to track what's being oxidized, what's being reduced, and going from one to the other. How many electrons is that atom gaining or losing? Next is going to be this manganate. So that's a little more difficult. It's not a monoatomic ion. How do we assign that? We actually have a set of rules. So when we have multiple non-metals, they're going to go in a certain order of precedence, with fluorine at the top, then hydrogen, then oxygen, then group 7A, 6A, etc. Fluorine, if it's taking precedence, is going to be a -1, hydrogen a +1, and oxygen a -2. So typically what we're going to see is oxygen is a -2, although not always. If it's paired with fluorine or hydrogen, that oxidation state may adjust because fluorine and hydrogen are higher on the table. They take precedence over that. But in this case, we're going to say or assume the oxygens are all -2s. And this whole thing here totals up to a -1. Let's see. Where's my fancy? There they are, colors. Yeah. So I've got that -1 right there. So I know all those oxygens combined, whatever their oxidation states are, times 4, plus the oxidation state of the manganese is going to have to be -1. And in this case, we have 4 oxygens. So what that means is whatever the oxidation state of manganese is, plus 4 times -2, because we have 4 oxygens and each oxygen is -2, that's going to have to add up to -1, the charge overall for this polyatomic ion. So the only thing manganese could be in this case is a +7. So within that polyatomic ion, our oxygens have an oxidation state of -2 each, and then the manganese is a +7. So now I'm going to look at what elements do I have on the left and the right, which ones have had oxidation changes. So that is the manganese went from a +7 here to a +2. So it became less positive, more negative. How did it do it? It had to gain 5 electrons, right? And the iron went from a +2 to a +3. So each iron had to lose 1 electron. This was reduced. This was oxidized. I can break those out and write them as half reactions if I want to make sure I'm accounting for everything and I can think about how many electrons overall I have. So if this gained 5 electrons, the electrons are going to be on the reactant side, and that's going to get us to our product right here. So this is the half reaction for just the reduction. Now, again, things don't happen in a vacuum. I can't have reduction without oxidation. So we are going to come back and do that oxidation as well, and then we're going to combine them. But for right now, let's balance this reaction. Let's start by looking at the element that's being reduced, the one of interest, the manganese. I have 1 manganese on the reactant side, 1 on the product side. So that's good. We're good there. We don't have to do anything further there. Now I look at, I'm accounting for the electrons next, the 5 electrons. Then I have to look at, are there any other elements? And there are 4 oxygens. And again, we can't create those or make them disappear. So I have to get 4 oxygens on this side as well. When I do this in acidic solution, what I'm going to do is I'm going to account for those oxygens by adding water. And if I need 4 oxygens, I would add 4 waters. So there's 4 times the single oxygen and water. Now I have 4 oxygens on the right and 4 on the left. But you've probably noticed now we have 8 hydrogens here on the right-hand side, on the product side, that we don't have on the reactant side. And I'm going to account for those by adding those acidic protons. And that's why it's balanced in acidic solution. So this should be the final balanced reduction half reaction for this manganese. I have 8 hydrogens on each side. I have 4 oxygens. I have 1 manganese, and I'm accounting for those 5 electrons that the manganese gains to change its oxidation state. Now we're going to do the same thing for the iron. So I've got my iron 2 plus. That goes to become iron 3 plus. Irons match. That's good. 1 iron on each side. I don't have to do anything to balance them. I do have to account for that electron that it lost, though. So I'm going to put that right here on the product side. And now this is completely balanced. There's no oxygens, hydrogens, anything like that that I have to worry about. Okay, but now I have to combine these 2 reactions to get our final reaction. And normal rules apply. I can cancel whatever is identical on the left-hand side of one reaction to the right-hand side of another. At the moment, that would only be the single electron. What I need to do is within that redox reaction, I want to make sure those electrons are balanced. So however many electrons are being transferred in one, I need to transfer that same number in the other. So here, this is gaining 5 electrons. So to provide those 5 electrons, this has to lose 5 electrons. Here, let's give ourselves a little bit more room. Okay, but each iron, as we established, is losing 1 electron. So if I'm going to provide 5 electrons, then I need 5 irons. 5 irons, each iron loses 1 electron, times 5 gives me my total 5 electrons lost. Now the electrons from my 2 half reactions match. If anything else, so I can cancel those. They're identical on the left-hand side of the reaction to the right-hand side of this one, so I can cancel them. If I had waters or acidic protons or anything like that, I could do the same thing here. But otherwise, that's the only thing that cancels. Now I'm just going to add it up. So I'm going to keep everything on the reactant side of both reactions, combine them. And that is my overall redox reaction in acidic solution. So those are just going to take you through all those steps, everything important there with assigning oxidation states. So let's go back to our slide. You can see why we have these 8 hydrogens here now, 4 waters. Why didn't we just add 4 oxygens on the right-hand side to balance this, etc. And why or how do our charges balance? Okay. So yep, we can split this into our half reactions, balance those. And there's no, as it mentions, free electrons. Something has to be providing them, something else has to be taking them up, and that number is going to be equal. We wouldn't have something providing 4 electrons, something only taking 3, and then just have a free floating electron there. All right, so let's look at another reaction. Let's look at another possibility that you're going to be hit with, which is balancing this in a basic solution. Let's try, yeah, I think I like this one. All right. So we have zinc, hypochlorite, and again, this is in not acidic solution now, but basic. So let's start again by assigning oxidation states to everything. I have zinc right here. Zinc is a metal. There's no charges. This is a solid. So this is the free element in its naturally occurring state. It's going to have an oxidation state of 0. Chlorate, if you remember our table of precedences, we have fluorine, then hydrogen, then oxygen, then group 7A below oxygen. So oxygen is going to take precedence over the chlorine. It's going to be a -2. Overall, this whole thing adds up to -1. So what would we have to add to a -2 to get a -1? We would have to add a +1. So the chlorine here is a +1. The oxygen's a -2. Zinc hydroxide. We could break apart the hydroxide and do the oxygen and the hydrogen by themselves. But since this is ionic, the hydroxide we know is a -1 charge. We can just keep it that way. So I could just write a -1 here or above it or wherever you want to do it. But overall, that OH, actually we have oxygen, sorry, we should break them apart. So let's do that because we do have that oxygen over there. All right, so hydroxide we know, I'll just write it down here for now, is a -1 charge. The both nonmetals, oxygen, hydrogen, we go back to our table of precedence. Hydrogen is going to be a +1, and for this to overall be a -2, oxygen would be a -2. -2 plus a +1 gives me -1. So -2 for the oxygen here, +1 for the hydrogen there. Overall, this has a -1 charge. this whole thing is charge neutral. So what would the charge on the zinc ion have to be? Well, if I have two polyatomic ions with a -1 charge and only one zinc, the charge on the zinc would be a 2+. So it's ion, single monoatomic ion. Its oxidation state would also be +2. And then monoatomic ion here for the chloride, -1. So its oxidation state is -1. So if we look at these, what changed? The zinc changed. It went from a 0 to a +2. Oxygen did not change. It's a -2 on the left-hand side, -2 on the right-hand side. But the chlorine did change. It went from a +1 to a -1. So for this to go more positive, it had to lose 2 electrons. And for this to go from a +1 to a -1, gain 2 electrons. One electron is going to take us from a +1 to 0, and the next electron is going to take us from a 0 to a -1. All right. Let's break these apart again. Let's look at just the oxidation and just the reduction. Or we'll copy it the way we did before, I guess. We started with reduction on the previous one. So I have ClO-, and then we have Cl- here. We know that it was reduced. It gained 2 electrons, so we're going to put those right here. Each chlorine gains 2 electrons. Chlorines are balanced. Now I have to balance out those oxygens. So we're going to go through the same steps. We're going to start by adding that many waters. In this case, that's a single water. I need 1 oxygen, so I only need 1 water to get that. Now, if it were acidic solution, we'd account for our 2 hydrogens. I'd add those right here, and everything would be balanced and we'd be done in an acidic solution. In a basic solution, I want to neutralize all the hydrogens with hydroxides. So how many hydrogens do I have? 2. So we're going to add the same number of hydroxides. These 2 hydroxides are going to react with neutralize these 2 H pluses. And I can't create or destroy matter, so I have to account for the 2 hydroxides on the left-hand side. I'm going to add the same number on the right-hand side to balance it. Well, you're probably saying, wait a minute, if this is, an acid-base neutralization, I know that gives me water, and I know OH plus H is water, so can I just rewrite this as water? Yes, that will probably make your life easier. So I can do 2H2O plus Cl minus plus 2 electrons goes to give me Cl minus plus H2O plus 2 OH. Now, the other thing, yeah, this should work, is if I want, I can kind of save myself some time and I can actually cancel out some of these waters. I have 2 waters on the left-hand side and 1 on the right. So to simplify this, of course, I could get rid of this and get rid of 1 of these, and it should still be balanced. I've got 2 hydrogens and 2 oxygens on the left-hand side, 2 hydrogens, 2 oxygens on the right-hand side, 1 chlorine on each side, and I'm accounting for the electrons. So this is technically my balanced reduction reaction in basic solution. And then we're going to do the same thing for the oxidation, the zinc. So I have zinc, solid, oxidation state of 0, goes over here to the zinc hydroxide. And in this case, it is losing 2 electrons. So I'm going to put those right there. The element being oxidized, the zinc matches, 1 on each side. Electrons match, we're good. Now I have to account for these oxygens and hydrogens. So technically, we'd probably be able to, we could shorten this, but we'll go through all the steps. I have 2 oxygens on the right-hand side. So we're going to add 2 waters here. That's going to balance our oxygens. I have 2 hydrogens as well, but 4 over here. So I'm going to have to add 2 hydrogens over here to balance it. And if this were an acidic solution, we'd be done, but we're in basic solution. So I have to neutralize all those hydrogens with an equivalent number of hydroxides. And again, we could just take the 2 OHs and the 2 H's and rewrite that as 2 waters. And you'll notice, to simplify this, I have 2 waters on the left, 2 waters on the right. I could just cancel those out. Now we notice this were just OHs. We probably could have skipped all those steps and just put the 2 OHs on the left. But I wanted you to see all the steps. All right, now finally, we look at our half reaction for reduction, half reaction for oxidation. Do the number of electrons match? Yes. So I don't need to multiply the top or the bottom by any factor. I can just go through and add these. And I'm going to cancel everything on the left-hand side that matches everything on the right-hand side. So in that case, that's these 2 electrons, these 2 OHs, and nothing else appears to be identical. So let's add that through and see if we did this properly. So I've got H2O plus ClO minus plus zinc goes to give me Cl minus plus zinc hydroxide. 1 chlorine on each side, 1 zinc on each side, 2 oxygens on each side, 2 hydrogens on each side. Yep, that's our final balanced redox reaction for this in a basic solution. So do a lot of these. I recommend doing these practice problems. Use this as a reference. Review it, slow it down, speed it up, whatever you want to do. Hopefully this is helpful. I showed you how to do both acidic and basic, how to assign those oxidation states. Remember, those rules are on page 195 of your book. But you'll need to practice those. You'll want to do at least a few more acidic and basic solutions. So you can, 1, assign oxidation states pretty quickly, and 2, balance them in either state pretty quickly. All right. So yep, this energy then is provided by this movement of electrons. And especially we'll see later, if this is a spontaneous reaction, it's going to happen all on its own without any additional intervention from us. And that's going to produce or give us that flow of electrons, produce energy and heat. And we're going to be able to use that energy to do work, to drive another reaction or to move something, or store that as a battery. So we're going to look at, how do we do that, I guess? How do we make use of that chemical reaction? And how do we sort of harvest those electrons that are flowing to provide energy or do work for us? So we're going to look at a galvanic or voltaic cell. Same thing. We're going to separate the thing that's being oxidized and the thing that's being reduced into half cells. And we're going to use that reaction to sort of work for us. So you can see these are actually essentially separated. So what's going to happen is, because this is spontaneous, this reaction is still going to occur without any outside intervention. But the electrons need to transfer. They need to go from the thing that's donating them to the thing that's taking them. And what they're going to do then is flow through this wire from this vessel over to this vessel. So as this thing is being reduced, this is the reducing agent. So as this thing is being oxidized and losing electrons, they're being provided to the thing that's being reduced, and the reaction is still going to happen. We're going to see both the oxidation and the reduction, and it's these electrons flowing through this wire because we've separated the half reactions that's going to provide the energy or the work for us. And in this case, yeah, still same cell. Okay, so a few things to note, and we'll break this down a little bit more as well. Reduction is always going to occur at the cathode, and oxidation is going to occur at the anode. So if you can follow the flow of electrons, you can see what's being reduced, and that's our cathode, and what's being oxidized, that's our anode. All right, so in this case, we'll look at specific reactions and specific things being oxidized or reduced. So in this case, we're going to be oxidizing zinc. So it's going to be losing electrons. So we're going to be going from zinc in its free state, naturally occurring state, zinc 0 to 2+. And in that case, 0 to 2, it's losing 2 electrons. And where are those electrons going? They're going from this connecting wire across to the cathode. So what that means is we're carrying out this reaction. We're losing or we're reacting zinc and producing this zinc ion. So actually, the mass of this anode would slowly start to decrease. Zincs are going to come off. And the concentration of zinc in this solution, zinc 2 plus the ion that's soluble, is going to increase. And those electrons are going to flow through over to here. Here we have the reduction reaction. So that's going to be the gain of electrons. So I've got ions in the solution, copper 2 plus ions. They're going to gain electrons and go to form that free element, the copper solid, copper 0. And in this case, it's going to be plated as it's making that copper metal. As we're going from that dissolved ion to the solid, it's going to plate all along that cathode. So here we're going to see the anode slowly losing mass and the concentration of the ion in the solution increasing. Over here, we're going to see the cathode slowly gaining mass and the ion in the solution concentration decreasing. We can't have ions by themselves. I can't have positive ions. I can't have cations without anions. That's the sulfate right here. And the same thing over here for the copper. And I can't get an unbalanced ratio. I can't have less cations than I'd have anions, or I'm going to start to get a charged solution and get electricity arcing within that solution. So we have to have something as we're adding positive ions here and taking away positive ions here. I have to have something that's going to add or remove positive or negative ions to keep that balance. And that's going to be something we call a salt bridge. Could be any other ion, but as we're producing positive ions here, it's going to put more negative ions into the solution to keep them balanced. And as we're removing positive ions from this side, it would be putting positive ions into the solution again to keep them balanced. Yep. So we'd have a net ionic charge accumulate unless we have some type of migration, and that's what that salt bridge is going to do. And this could be whatever. It could be the same, it could be whatever, sodium sulfate or sodium chloride or potassium iodide, but it's got to be some salt solution that's going to put more positive and negative ions into solution so we don't get a charge imbalance. And that's our salt bridge right there. And you can see it makes contact with both of these so that the negative ions could flow into this side and the positive ions could flow into this side. And where are we? And I think that's as far as we were going to get at this moment. So really focus on those balancing half reactions, acidic basic solutions, and then start to at least look at these galvanic cells. And you don't have to figure everything out about them, but know what the anode and the cathode is, kind of be able to figure out where's the oxidation reduction occurring, which direction are electrons flowing, and what is the purpose of a salt bridge. Know the definition of a salt bridge. So hopefully this was somewhat helpful. I'm going to do one more thing for you, again, as a way of apology. I'm sure this has been very boring and painful, but here we go. If you would like to reach out to me, if you have any questions, you're welcome to email me at matthew.rex@ucf.edu, or if you would just like to yell at me for not being in class yesterday when I was supposed to, feel free to shoot me an email and yell at me. If you want help on these face-to-face, I'm going to give you all my office hours. Tuesdays, I have office hours from 10:30 to 11:30. Wednesday, I have office hours from 1 to 3. Thursday, I have office hours from 11 to 12. And Friday, I have office hours, or sorry, not 11 to 12, but 10 to 11. And Friday, I have office hours from 11 to 12. I'm in the chemistry building. Room 208. So you already have Dr. Kubler to help you, but if for some reason he's too busy or his office hours at a time you can't make it to, I'm going to provide you with all my office hours. Come in with any Chem 2 questions. I'll happily, gladly help you. Again, I apologize for not being there yesterday. So I'll stop the video here, and hopefully this was somewhat helpful.